I will continue to haunt you remotely. So just a reminder of some of these issues. Homework 9 went out yesterday, and then that'll be due on Wednesday. And here's, I guess this is number 8. And yes, review session Wednesday at 8 p.m. We talked about that last time. We talked about the exam last time. This is new information, though. I think that we'll have a review session for the final exam, and then I'll return midterm number 3 the day before the exam. So Monday the 11th at 1 o'clock, EBU room 331. So if you want to come back and get the midterm 3, we should have it graded by then. Okay? Yeah.
So for homework 9, number 2, it says a cube octahedron.
That's it.
How do you draw this?
Cubo-octahedron, yes. Did you read Tau chapter 6?
Page 34.
This is directly from the book. Yeah. So a cube octahedron, so that is a collection, and we're going to talk about that today. What that looks like is something like this, right? Where you have a mixture of both cubes and triangles on a multifaceted surface. Yes?
For the review session, how long will you be there?
When there are no people, okay, what's your situation?
I have a final on Monday from 11:30 to 2:30.
Okay.
So I don't know when.
If there's nobody there, I'm going to leave. Like if everybody gets their stuff sorted, but I'll still be in my office until about 4 or so. Okay. And then also, Rosie, what's your office number? Because she'll have the midterms. It's
My oldest number.
yeah.
343C.
343C, because she'll have the finals too. She will have the finals. Okay. Okay. Location of the final. When I pulled it up here, it says TBA, but I asked the business office and they said it's this room. So unless you hear otherwise, I'm assuming it's still going to be in this room. Okay. So today we're going to do 2 things. One, we're going to continue our discussion of surface stabilization. 2, then is we're going to talk about actual chemistry. We have talked very little about organic chemistry in terms of doing chemical reactions, but we're going to talk some about the most common pieces of organic chemistry or chemical reactions that you would do that are common in nanotechnology. And then on Monday, the remote lecture that I'm going to send it's a lot of literature examples where people have done this bioconjugation to make higher ordered assemblies of nanoparticles using some kind of covalent chemistry rather than making crystals between atoms. So hopefully that will be of interest. Okay. So we talked about that surfaces come at an energetic cost. We talked about that curvature can further decrease this thermodynamic stability. Surface area to volume ratio of nanoparticles equals these higher surface areas, more energetically disfavored, and so that's why they like to recombine to reduce the surface area. And so we got through some discussions of how solid nanoparticles stabilize themselves, or tools that we can use to increase the stability of particles, including decreasing the ionic strength, and then we talked about polyethylene glycol. And so today we're going to talk about some more of these different techniques. Okay. So polymers, we talked about polymers as we're essentially sterically repelling the particles from coming together, right? We're physically preventing them from touching each other. And we're sort of artificially increasing the electric double layer by creating more of a shroud of water and charge around those materials. Adsorbates are kind of different. And adsorbates we're essentially doing more of chemistry. We're altering the charge, or we're altering the electronic state of the particle. That's what we mean by these adsorbates. And it'll make sense when we go through a couple examples. Whereas adding a polymer, it's more of a physical method, right? Do you guys know what the word sterics mean? You've seen sterics, right? It's like room. How much room do you have? Physical sterics, right? Whereas absorbates is more chemistry, and that's why I put it in quotes. So we're modifying the surface energy, the atomic structure, or the surface chemistry. So let's look at gold. And you've seen this probably before, where we can use sodium citrate as a gold capping agent onto nanoparticles. And that citrate can also act as a reducing agent. A reducing agent is an electron donor or acceptor? Donor. Yes. An electron donor. And does that make sense? Because we're normally making, when we start with gold, it's a gold salt. And so it's a salt of, gold in that situation is a cation or an anion? Cation. It's a cation, right? We generally have some kind of AuCl3 or something of the sort. So we've got all this Au plus or plus plus or plus plus plus. So then we need some kind of electron to reduce this into gold metal, right? And so by using citrate that has a lot of electrons, they can also, in addition to being an electron donor, then can also chemisorb to the surface through these anionic interactions, okay? Yes?
What does chemisorb mean?
Electrostatic, basically. Yeah, it's another word for electrostatics. Yeah.
Like, what is the ion physical? Does it like attach to the gold because of an electronegativity difference?
Yes. And so if you look in the book, this is the figure that she had in the book, and to me this was kind of confusing, right? Because this is sodium citrate, okay? And so we've got lots of negative charge, right? We've got negative charge everywhere. And then there's this interaction between the surface and the gold. And then, but you look over here and the surface has all of this negative charge. So it's kind of confusing. Why would this negatively charged thing want to be attaching to this negatively charged surface? But with this, a better way of thinking about this is how you start with gold 3+, and over time move it to gold metal, right? And that this sodium citrate is an electron donor that's not only donating electrons to condense this reaction, but then is also immobilized on the surface. So the surface is not entirely gold metal, right? You're going to have some, or excuse me, gold metal. You may have some that has a minor positive charge. And so it's this interaction of the sodium citrate with that surface then that leaves the overall surface with a negative charge because of this the strong electron density on all of these carbonyl groups, right? Yeah.
So how do we start with the particles of gold ions? The ions don't really hang out together.
We don't. We don't.
So what was that gradient that you showed us? Yeah, that one.
So think about this as what percentage of the total gold in the system is existing as a gold 3+. At the beginning, it's all solution, 0 nanoparticles, and then over time, we have less and less and less as an ion, and more and more and more as a metal. Yeah. So then the other thing that this can do is it kind of passivates or stabilizes the surface, because there's essentially no further growth for additional, or no room for any additional gold to coordinate. Right? If we've got this layer of sodium citrate on the surface, there's no room for or binding sites for additional gold to come in. It enhances the solvation because it has this very electron-dense cloud of carbonyl groups, and so that will create a strong electrical double layer, which we know strong electrical double layer increases stability. Okay? Another common example is with quantum dots, and where we take a cadmium selenide core and then wrap it with a zinc sulfide coat. And so here, we can think about this doing two things. We can think about it stabilizing the particle, but it's also increasing the nanoparticle's functional behavior. So we know that these quantum dots have what's the density of states of a quantum dot? It has 2 states, right? And so I don't know if you can see it here, but it has a line here that's labeled VB and a line here that's labeled CB for valence band and conduction band, right? And so you can see the hole and the electron, right? And so if we just have this cadmium selenide core, there can be many sites on the surface of the particle where this electron hole pair can dissipate through non-radiative decay. So it can interact with the solvent, it can interact with maybe dissolved oxygen that's in the solution. There's lots of potential to have some other pathway of that electron recombining with the hole other than fluorescence. Okay? That makes sense, right? That there can be these competing pathways to relaxation. So what people do is wrap this with another layer, most commonly of zinc sulfide, that has an even higher conduction band and valence band. The band gap is bigger, right? And what that essentially does is forces that electron hole pair. That's the only way that we can get rid of that energy difference, is by fluorescently recombining the electron and hole in the in the cadmium selenide core. Okay? So this is what this is showing, is how stable is the fluorescence excitation for cadmium selenide or cadmium selenide when it's wrapped with that coat. Yeah.
So does the increased band gap kind of act as a gatekeeper for emitted photons?
That's a great word. I think gatekeeper is a great word. It's kind of more like trapping it. We might want to say it's trapping it, where there's no other route for it to go. I mean, gatekeeper kind of implies that there's a decision to be made, and it's not really making a decision. It's kind of forcing it into one pathway. Yeah.
What did you mean by fluorescently recombining?
I just meant that the electron and the hole combine to give off a photon, as opposed to this electron could go into oxygen in the solution. This energy could be given off as heat into the solvent. It could be given off to maybe phosphorescence. There's a lot of other radiative pathways non-radiative pathways that it could take other than fluorescence. Yeah.
If you don't mind explaining, why did you cut it with the zinc again?
The zinc does is it has a higher band gap. And so because it has a higher band gap, it restrains the ability of this electron hole pair to decay through other methods. Because if it, what's another way of saying that? It essentially is trapping that exciton. This electron hole pair is an exciton. It's trapping that electron hole pair into a state in which it can only relax via fluorescence. Okay?
So once you wrap the original quantum dot in zinc sulfide, is the exciton still localized in the cadmium selenide, or is it
Yeah, that's a good point, because we had talked about this electron hole pair acting as an artificial atom itself, right? Like as an exciton. And the answer is yes, it does trap it inside of this original cadmium selenide. And it has to, right? Because this band gap is higher, right? It doesn't have the energy to move out into this, the higher band gap of the zinc sulfide, right?
How is it still able to be excited by light? No, it's.
You're saying how does a photon physically get through that dimension? Because that light is much more energetic. Think about this light. This excitation light is UV, but this is going to be generally, I don't know, green or red, based on what's going to govern whether it's green or red. The size. And if it's red, it's going to be bigger or smaller? Bigger, yeah. So this incident photon, the excitation photon, has enough energy to excite and to pass through here. Yeah. So band gap ZNS bigger than band gap CDSE. Cool. Yes?
So why wouldn't it just decay like thermally, for instance?
In terms of thermally relaxation into the solvent. Don't get me wrong. We're not having like 100% quantum yield by doing this. It just increases it. Yeah, we're not achieving a situation where every single excitation event leads to fluorescence, but we're significantly increasing it. Yeah.
So is the zinc sulfide effectively transparent to the emitted photons?
Yeah, that's a good question. Yes, it has to be. And what's the physics of that?
Because of the band gap?
Because,
to be able to excite an electron?
yeah, right? Because there's no way that it can absorb because it has less energy than this higher band gap of the zinc sulfide. Yeah. Sweet. Okay, other topic that we see and that stabilizes particles is surface relaxation and surface recombination. And again, this was kind of following up on the notion that it's very rare that we actually take a slice through bulk material and it behaves that way. So both of these are notions that if we have this idealized FCC or BCC crystal structure, that there's changes on the surface that the material does to achieve a lower energy state. So surface relaxation is a type of bond contraction, where the spacing between the first and second atomic layers of a surface are smaller than the layer spacing observed in the bulk material. Okay. No change in the periodicity parallel to the surface or the surface symmetry. The degree of contraction is inversely proportional to the number of broken bonds, NB, the number of broken bonds of the surface atoms. And there are normal or lateral. Okay, so relaxation, we're not forming any new bonds. That's one of the key things. And in reconstruction, which is going to be the next topic, we do get some new bonds. Okay, so let's look at an example. So if this is our bulk material and we cut some kind of area right there to expose this new layer, this atom here, right, is still experiencing forces from all of its adjacent neighbors, right? But this one here is flipping out because it doesn't have as many buddies anymore, right? So what it can do is move closer to the buddies that it has, right? It doesn't have as many friends, but it can get closer to the friends it has. And so that's what this thing is doing right here, is that you can see how these are roughly equal, right? But this has tightened up and effectively increased this layer, right? Similarly, you can get a lateral movement side to side. So here, this spacing has remained the same, but there's just been a minor shift. Okay? Yeah?
In the previous slide, you talked something about gas part. Is this only in the gas phase?
No. So gas phase means like this area here. So this is the solid, and then Okay, so your question is, would this still happen in a liquid phase? Probably yes. Yes. The other thing you would have in a liquid phase is solvent effects, significantly more. The way people started seeing this is with scanning tip microscopy and a lot of fancy electron microscopy techniques, which is inherently done at really, really low vacuums. And so that's really the only way that people know for sure that this exists, is because of these microscopy techniques that are done at really high vacuum. But yeah, I don't know why this would not remain in solution. Yeah. Yeah.
Does the lateral shift cause any difference in its packing geometry?
Only on that very surface layer, right? So does this, relative to the entire nanoparticle? Not really, right? Yeah. Yeah.
So, how far down will the relaxation go? Because
My understanding is that it's only on the very surface. So you could imagine that like this gets tighter and this is a little bigger and this is slightly bigger and this is just a smidgen bigger. You could maybe imagine that it's not drawn like this. But yeah, my understanding is that this is just a few monolayers, because if you're making a different crystal if that's not the case. And these are pretty stabilized, right? There's no reason for them to feel the need to do that. Yeah.
By how much does the layer shift?
Angstroms. It's not a lot, like 1 or 2 max. Yeah. Yeah.
Lateral relaxation, like a contraction of bonds, isn't like the bond length.
You can think about, so how is this a contraction of the bonds?
But isn't it getting closer to the one?
Yeah, I mean, it's getting closer to this one, right? The distance between this and this has contracted. So yeah. Yes.
Is this relaxation like a byproduct of electrostatic repulsion?
Yes, and electrostatic repulsion of what?
The 2 electrons in those atoms?
These electrons that are free on the surface, right? That no longer have another atom to coordinate to. Right?
How does the kind of orbital affect how its lateral shift?
How does the orbital affect how the lateral?
If you have 2 electrons versus 1, there would be, like,
I
can you
would
predict a trend with that?
Probably. You would think if you had if you had more unpaired electrons, you would have more of a shift. That's what I would predict. But probably at some point you have so many electrons that you start to do surface reconstruction, which is an alternative approach, whereas instead of having these kinds of unpaired electrons that are causing everyone grief to the point that they start to wiggle around, that you have a new bond forming between these surface atoms, okay? So the way that this is drawn is kind of confusing, because this is her schematic for surface reconstruction, where the original silica looks like this, but they all move in one direction in order to restabilize this structure. So when I first saw this, I said, how is this different than lateral? How is this different than a lateral relaxation? But what we're having happen here is we're forming a new bond between adjacent atoms, and not all of them are moving, right? So if you look at this row here, has not moved, but all of these have moved. Whereas in a lateral relaxation, we have some kind of shift of an entire surface layer. But in a surface reconstruction, it can be periodic, and we're forming new bonds, okay? Yeah.
With this, like in my head, 2 issues come up. One, how like if you're cutting bulk material, it's never necessarily symmetric over the surface that's exposed. So you'd have like bumps or anything like that. So the shifts would be more random than just saying, oh hey, all these atoms are moving like this.
Totally.
Something like that. And then the other is, with this surface reconstruction, that would not necessarily be as symmetric as that also, just because if one of the exposed surfaces is like a mountain versus something else, then you'd have surface reconstruction in one part and then lateral movement in another.
Yes. I mean, I think it's fair to say that you could definitely have both. And then, so this is an image of a gold surface that has reconstructed itself. So you can see how it's very periodic, right? And if this was just a FCC, I mean, you know what an FCC structure should look like, but you can see how these gold atoms have pulled closer and closer together here and farther apart there. There's just less electron density. So yeah, it is, you definitely get periodic structures.
Is there a way to calculate the, like you could see some holes in there if you look closely?
Like here or there?
In between those lines.
Yeah.
So is there a way to calculate how that's gonna like structure itself, or is it just random?
People do diffraction patterns is the way to do it, is you look at the diffraction pattern of your particle, and you can start to get some estimates of the bond lengths. Yeah.
So are these in equilibrium? Like, are these moving?
I don't think so. But I don't know for sure. But my understanding is that after a surface is made, that's when this occurs. And that once it's achieved equilibrium, unless you perturb the system, it seems unlikely that this is going to be a dynamic.
So
Especially for reconstruction, where you're forming new bonds. These bonds are not going to be forming and breaking.
for relaxation, does that have anything to do with like Raman scattering?
You could probably change how much, how strong the plasmon is based on how close those gold atoms are to each other, but not directly. Yeah. Okay. So what else can we do? Low energy shape. So this is another kind of approach-ish that nanoparticles can take. So previously we showed that there's a hierarchy in stability, and that in face-centered cubic, a 1-1-1 plane is the most stable, followed by 1-0-0 and 1-1-0. Because 1-1-1 has the, yeah, which is, yeah, the say it again?
Nearest broken bonds, the lowest only 3.
It only has 3 broken bonds, right? It has 3, whereas these guys have 4, 5/6. Okay? So therefore, nanoparticles would want to have a 1-1-1 crystal face. Okay? And so this is also from Tao chapter 6, where she looks at different materials, gold, silver, platinum. No, I said that wrong. Silver, gold, platinum, and how you can make these different shapes that have these different crystal facets. So you might be wondering, okay, so you said that 1-1-1 has the lowest energy, and so this one has the lowest energy because it's all 1-1-1. So how would you ever make this one? Why would you ever make this one if it has higher energy?
Is that also like how gems are cut, I guess? People like lowest energy.
Huh.
Well, I guess it gets corroded. You're making a new surface.
You are making a new surface. I mean, I think the way they cut gems is to optimize how the light goes through it, right? And so there it's a function of, because emerald has a very different crystal structure probably than diamond, right? So I don't know that you cut a diamond differently than an emerald, but I would think that you would.
But growth matters like on stability.
Growth matters on stability, yes. Yes.
Why does the nanoparticle for the different materials look so much different?
That was my question. That's what I was asking you. It's like, why, how, or why could you ever make this one if this one's so much more energetically favorable?
I was saying, like, why does like 1-1-0 or like 1-1-1 for silver look so much different than just for gold?
Oh, you're saying why do these look different? Well, I mean, for one, they're very different materials. What are the scale bars? They're not labeled. That's like my biggest pet peeve.
Because I label the bottom one says like maybe it's more than
No, those don't look like they're the same.
Can you not make nice shapes like that with flat and make it count? Some ones are pretty nice.
I mean, these are very monodispersed, but they are, excuse me, these are very monodispersed. These are kind of a mess. They're also kind of fuzzy. It's experimental technique, I guess. I mean, yeah. How clean is your glassware? And but seriously, how would you make these, if you wanted to, so you have the exact same gold chloride starting material, how would you push it into one direction or the other?
We talked before about how we would make the rods, right?
Yeah.
By conjugating them in different ways or by
So,
surfactant.
okay, so a surfactant, that's a yes, that's one answer. What else can you do? Yes.
Increase the energy of the system,
By
temperature.
temperature, there's an option. What's the third one?
Kind of in line with capping agents, you pick capping agents that are more prone to interact with certain surface energies.
Yes, yes. But think about when we were talking about sodium citrate, which is,
With electricity,
okay, work on that. Charge.
Ions.
more charged salts.
The choice of your reducing agent, right? If you have a really, really strong reducing agent or a relatively weak reducing agent, then you're putting more or less energy into the system. You're changing the, so if you have a super strong reducing agent, you can start to push it into these more energetically disfavored systems. Or if you have some temperature into the system, then you can start to put it into these energetically disfavored systems, right? And I think part of also what you're seeing here is that, again, over time, this is not a very well passivated system because you're still getting gold salts from the system that's still decorating on the surface. Yeah.
So why would just, if you use stronger reducing agent, I understand like it would maybe make the probability more equal,
Mhm.
so you maybe have an even distribution of all three, but why would it favor?
Only one. Because you've pushed it beyond the point of, you've put enough energy into the system that it's sufficiently, you're saying why don't you get a mixture of all three of these?
Yeah, why is that one now more preferred? Is it like more stable surface area or something?
Yeah, I mean, it's a combination of capping ligands too. I mean, so perhaps you've included some surfactant that is going to block any particles that start to develop that 1-1-1 surface. Yeah, yeah.
Is a 1-1-0 orientation achieved before a combined 1-0-0-1-1-1 orientation?
I don't think you can make any firm, I mean, it all depends on your synthetic conditions. Yeah, yeah, I don't think you can make any strong statements on that.
Not even though like you can like predict the energy of the broken bond of your nanoparticle?
Say your question again.
Like what orientations would be preferred to form before others? Like 1-1-1 is the least energetically.
Yeah, I mean, it's most likely to form when you're putting individual
So, like, as you
ions
increase the
together.
energy of it, like would you end up getting 1-1-0 before you combined 1-0-0-1-1-1, or like what's the order in which these structures form?
Again, I don't think you can. Yeah, I think you have. It's based on all of these parameters. Yeah. Was there one other? Yes.
So what is making like a cubic nanoparticle, like how does that function versus making a bacteria?
Generally, it's the plasmonics, how it interacts with light. That's one of the most interesting. What else? So people have done where you can just assume this is a cube. And you can get them to self-assemble in this way versus this way. And then you can start to do interesting things with light in terms of how these assemble when you make them into chains like this based on the kinds of surfaces that they have. So you can make chains of these things. And so then that starts to change how it modulates light. Yeah. Yes?
So is the actual size of each cube depending on the time they let them react?
Most of the time, yeah. That's your biggest. I mean, these things generally increase for a couple hours, and then that's about it. You can quench them if you get a right size, but they're generally not very stable. So it's generally a better idea to change the amount of your starting conditions and let it go to completion, right? Because to try to quench crystal growth generally ends up with bad crystals. Yeah. This one, okay, so then we can also think about twinned surface. So twinning is this orientation where individuals in the same crystal phase twin. And so they're no longer exactly in the same crystal phase, but rather they form a mirror image. Okay, so what's a good example? Like, let me turn the light off. So these would be twinning planes. If you look at this plane, it's a mirror image on either side of this line. Okay, so you can get these particles that they're no longer a single phase crystal, right? That's the main point of this, is that you take something, because this is a different phase than this, right? Even though it's one big particle. So you take something that should be a single phase, but it rearranges itself in order to have these different phases, okay? That have these mirror image planes, yeah.
By phase, do you mean orientation?
Orientation, yeah, it's probably also appropriate word choice, yeah. Okay. So now bioconjugation, we'll see how far we can get. So this again, this is chemistry. This is putting something onto a nanoparticle, where that something is a protein, a drug, an imaging agent, a whatever. So some of the things you want to ask yourself before you do this: what's the ratio of that thing to the nanoparticle? Where do I want the thing? Do I want it on the surface? Do I want it on the interior? Do I want it to be stable, or do I want it to be labile? Do I want it to come off at some point, or do I want it to be there forever? How pure do I want it? I'm sure you could think of many other questions. This is a screenshot that I took out from a review that I like, and this is specific to imaging, but you can think about the steps to building a nanoparticle contrast agent in some kind of life science application involves a lot of steps, right? So first you're thinking about your biochemical pathway, you're thinking about the target. If you're thinking about imaging, you're thinking about the imaging modality. If it's a therapy, you're thinking about the drug. And then there's the chemistry, right? There's some kind of chemistry, some kind of labeling. Then you do tissue culture, small animal, large animal, people, blah, blah, blah. They all have to work together, but the chemistry is really important. And it's really difficult, especially in nano, in terms of reproducibility. That's one of the biggest questions that FDA always asks, is how reproducible is your particle synthesis? And then you're doing something else on top of it, right? So simpler is always better. So just bear this in mind. Okay, so bioconjugation, that's what we mean, is if this is our nanoparticle and this is our ligand or our drug or whatever, it's this step right here, right? So this is in the scope of all of this, it's actually a very small piece, right? But it's actually quite important. If you go to graduate school and start working on this, this is a great text. I really recommend this textbook, Bioconjugate Techniques, and it has lots of good protocols, and I think you can even find the PDF. Okay, so if we had a PEG, if we had a pegylated particle, which we often do, this is a consideration in terms of our R's, right? Our R1 and our R2, because this is very important. So if we wanted to put something on the tip of the peg, like here, we would want to have a reactive R2, right? And similarly, if we want to react this PEG with the nanoparticle surface, we have to know both what this R is and also what the surface of the particle has to work with, right? But this is all tailored. When would you ever want to do this, where purple stuff is your thing? When would you want this to not be on the business end of the nanoparticle, but kind of like shrouded inside?
Anticoagulant?
An anticoagulant, some kind of drug, right? Some kind of drug. Whereas this would be a situation for a imaging, or, I mean, you could put the imaging agent in the center. So yeah, some kind of like ligand, something that's going to home this to the site of disease, right? So in this situation, in order to have room to put your cargo here, you would want a mushroom or a brush conformation. What do you think?
Brush.
Why?
I guess, yeah, the mushroom, because you need room for it to fit on the particle surface. So like,
That would be my answer,
the mushrooms are more
right?
spread out.
Yes.
But is it going to turn into a brush because you're increasing
Because now you're putting extra stuff there? I don't think so. No. So if you want to put your target on the surface here, then you probably need a lower PEG density just to have enough room. I mean, of course, there's lots of what's the example that I'm not showing here? There's another area to put stuff other than at the end of the PEG or on the surface of the particle. You can put it in the middle of the particle, right? Yeah. So, definitely don't think that this is your only option. There's lots of examples. This is drawn as if it's a gold particle or some kind of solid metal particle, but there's lots of examples where you have a polymeric particle.
If you were to put the drug in the center, how well will it diffuse through the PEG?
Pretty good. I mean, it's a function of your drug, right? So if it's a small molecule, you've got no problem. If it's a monoclonal antibody, that can start to be a problem. I mean, a monoclonal antibody is, 155 kilodaltons? That's pretty big. Yeah. So, yeah, I'm not aware of a lot of examples where they put a big biological drug in the center of a particle and use that for sustained release. And you don't need to, because those things already have such long circulation lives, right? You just inject monoclonal antibodies and you're golden. You guys know what monoclonal antibodies are? So let's just jump right there. So you take your stuff, whatever you want to have an antibody against, and you inject it into a mouse, okay? And your mouse flips out because it's got this new thing inside of it, right? And so it makes antibodies against this new thing, okay? So you can then draw the animal's blood and find those cells that have made an antibody against it. So say you want to have anti-MDMA antibodies. So you inject ecstasy into your mouse, and your mouse develops anti-MDMA antibodies. And then you collect the cells that are now presenting these antibodies on the surface, and then you fuse it with a tumor cell. Why do you think you fuse it with a tumor cell?
It grows.
It grows. Now, because the tumor cells will grow immortally, right? So once you make this so-called hybridoma, you can grow these forever, and you're going to use those cancer cells as a factory to sit there and make anti-MDMA monoclonal antibodies. It's amazing. If you... I was trying to find really good examples of... So I was trying to find absurd examples of antibodies, and so there are 37 anti-capsaicin antibodies available on BioCompare from 9 different vendors. So, I mean, literally, it's everything. There's like antigen or allergy profiles. So if you want to have an anti-oak pollen antibody, you can buy it. If you want to have, and of course, there's more biologically relevant materials, right? If you want the anti-epidermal growth factor receptor antibody, you've probably got 500 different choices.
So what you do to create antibodies, you inject some of the
For these kinds of, foreign bodies, right?
What about capsaicin? Capsaicin is like not bad, like something that our bodies are really not used to.
That's why it makes an antibody against it, right? I mean, because it's it's identified as a foreign agent.
But we like eat that stuff.
But it's not injected into your bloodstream, and that's what you're doing to this poor mouse. Is you're right? Yeah.
What is goat anti donkey?
Yes, great question. Okay, so
I'm not sure what that's supposed to mean as far as anti-donkey.
So this was a fun game that we used to play in graduate school because you can find all of these like gerbil, anti-mouse IgG, and so we were like, where's the pterodactyl anti-unicorn IgG? Or you could make up all kinds of fun ones. So that's the difference between a primary and a secondary antibody. Okay, and it's important. And so these are your structures of these are different immunoglobulins. You have IgG, IgE, IgA, IgM. These are mostly involved in allergies. By far the most common is IgG, immunoglobulin G. And they all have a structure that looks like a Y, okay? And it's 155 kilodaltons altogether. This region, the chain of the Y, or the bottom of the Y, is called the FCC because it's the fragment that you can crystallize. This region is the FAB because it's the fragment that actually is the antibody. That's the business end. So if we were to add this to capsaicin, the capsaicin would bind at that tip. It's amazing how much structural similarity you have between an anti-EGFR and an anti-capsaicin antibody. This is all the same. This is all the same. This is all the same. You just have a few amino acids that tweak on the very end of it, okay? So this region, if you made this in donkey, would be unique to donkey, okay? And so then what you can do is take some of this antibody, say you have, donkey anti-capsaicin antibodies, then you go back and inject that into your mouse again, okay? And then you can create a mouse antibody that's anti-donkey. What it means is that this mouse antibody is going to bind to that region, the FC region of any donkey antibody. So if this is now my cell that expresses EGFR, I have EGFR here, then I have this donkey antibody that's anti-EGFR, okay? Then I can come in with my mouse anti-donkey.
So now you have two antibodies.
Yes, and that's what a primary antibody is. It binds. Why would you want that? Doesn't this seem a lot more complicated? But people do this all the time. This is the secondary antibody, and that's the primary.
And if you attach another one to make tertiary?
I'm sure somebody's done it, but that's not common.
Functionally, why would a mouse need an anti-donkey?
Because it has this donkey antibody that's been injected into it, right?
Why do you want two of them?
That's my question. Can you think of any reason why you would want to have this secondary antibody?
Do you have two?
To disengage what the first one is doing?
No, because this is where it's doing its action, is on the tip, and you're binding on the FC region.
More binding sites?
More binding sites, which can give you more functionality or more. What you generally do this for is you can start to put more labels on this situation or more drug or more other stuff, and you get signal amplification. So say that your copy here, say the copy number is maybe 1,000 per cell. So then here you would get 1,000 primary antibodies per cell. But when you amplify it with this, maybe now we can start to get 5 secondary antibodies per primary antibody. So you're amplifying it a lot.
Why don't you get multiple primary antibodies?
Because there's no other binding sites for it to go to.
But there's lots of binding sites on those primary antibodies.
No, there's 2. 1, 2.
So then why can you bind so many lines, opposite antibodies to the primary antibody?
The number that you can bind, why can you bind so many here? Because the FC region is so much bigger.
Okay.
Yeah. If the region, it's comparing this region right here to that entire thing. Yep. Okay, we ran over time. So look out for Monday's video remotely.